Namaste. Namaste, friends. A hearty welcome to all my beloved friends. In the previous session, we have discussed a rare proof for Pythagoras theorem given by James A. Garfield, who was the 20th US President. Will you please observe the figure once again carefully? I am still wondering as to how Garfield could imagine a right angle triangle inside a trapezium. Wow, very great idea. Okay, people having in-depth knowledge with thorough understanding of this subject and having a clear vision can only do this. Okay. Okay. So today in this session we will discuss another interesting but highly intellectual proof given by a legend who made a revolution in the field of physics. Yes, he is none other than Albert Einstein. Okay, not by this Einstein, but by this young Einstein when he was just 12 years old, using the theorem of areas of similar triangles in a very clever way. Friends, this proof is the first and the masterpiece of Einstein. Masterpiece means a work done with an extraordinary skill, especially a supreme intellectual. It is worth to know the meaning of intellectual also. Intellectual means reasoning as well as understanding with regard to some abstract concepts. So probably Einstein at such an young age with this supreme reasoning and understanding could thought of a proof for Pythagoras theorem. Okay, and certainly this is his most accessible one. Accessible means reachable, so which can be easily understood by all of us. Okay, so it has taken about 40 hours of dedicated work to prepare this presentation. Please listen and observe carefully. Before we go to the proof, it is worth to know about childhood of Einstein and very surprising insights of the proof. There are two insights are there. They're wonderful. We are going to discuss that also in detail in this session. On November 26, 1949, Albert Einstein published an essay in the Saturday Review of Literature, which is a supplementary edition for New York Evening Post, in which he described two pivotal moments in his childhood. What do you mean by this pivotal moments? Means very big, important, critical moments of clarity that provides us with new perspective and opportunities to change our lives. So there are two important incidents that happened in his childhood. So that we are going to share now in the next slide. The first involved a compass needle that his father showed him when he was just 4 or 5 years old. Einstein recalled his sense of wonderment that the compass needle always pointed north, even though nothing appeared to be pulling it in that direction. He came to a conclusion then and there about the structure of the physical world. Structure means arrangement, relation. Okay, so he immediately thought of the arrangement and relation in the physical world. And he quotes something deeply hidden had to be behind the things. This is what he says. Something deeply hidden had to be behind things which need to be explored and understood. So probably at that young age only, he must have got some idea about the invisible gravitational force. So this is the first one. Now let's go to the second part. The second moment occurred soon after he turned 12 years, when he was given a little book dealing with Euclidean plane geometry. That is, Elements. The title of the book is Elements, having 13 volumes with 465 propositions. And regarding the book's lucidity, he wrote, so lucidity means written in a very simple language so that reader can easily understand and think with clarity. He writes that the idea that a mathematical assertion could be proved with such a certainty that any doubt appeared to be out of the question. Assertion means confidence. Okay. Normally the philosopher says, if you ask them a question, what do you mean by reading? They say this. What is reading? Reading means it is raising questions and removing doubts. So once Einstein started reading the 13 volumes of Elements, so many doubts appeared to him, and during the course they got solved. They were removed totally from his mind. With such a lucidity, the book has been written and provoked him to the wonder of a totally different nature. So he could get a different, altogether a different ideas to he went to a different world altogether. So that's how he was motivated by this book, The Elements. So I request my friends to download all the 13 volumes of The Elements. It is freely available, and please read them, each one chapter, carefully. Okay. So he concludes that essay with this beautiful thought. He says that pure thought could be just as powerful as geomagnetism. Pure thought could be just as powerful as geomagnetism. Friends, let us make our thoughts as pure as possible by becoming a sincere, honest students of our subjects, so that we can convey concepts to our students with a strong conviction. Okay? Yes. This is the image of young Einstein with the two beautiful quotes from him. Something deeply hidden had to be behind things. Pure thought could be just as powerful as geomagnetism. Okay. Now, as we already stated, the proof given by Einstein relies on the two insights. Relies means depend with full trust and confidence. Insight. What do you mean by this insight? It is worth to know it. Not having the deep understanding of the concept, but to have an accurate as well as a deep understanding of concepts. So the capacity to gain such a thing is called as insights. So this proof given by Einstein solely depends upon these two: deep understanding of some concepts which we are going to discuss right now. So we'll start with insight number 1. The first is that a right triangle can be decomposed into two smaller copies of itself. Copies mean something we can say that similar. Okay, you take any right triangle and we can divide that right triangle into two small right triangles, sum of whose areas is equal to the area of the given triangle. Okay, the figure will help us to understand. Here is a right triangle ABC, in which angle ABC is 90 degrees and BD is perpendicular to the hypotenuse, and this BD is dividing this whole triangle into two smaller copies of this triangle ABC. In other words, copies means these two are similar to each other and similar to the given right triangle. So that is the meaning of decomposing into two smaller copies of itself. You may wonder about the next sentence. And this property of decomposing a right triangle is the peculiarity of right triangles, which means that you can see this kind of a property is found in only in right triangles. It is totally different from the other polygons. Okay. If we instead, for example, to decompose an equilateral triangle into two smaller equilateral triangles, we will find that we cannot. So, Einstein proof reveals why the Pythagorean theorem applies only to right triangles. It is all because right triangles are the only kind made up of smaller copies of themselves. This is what he has written in that article. Okay, now let's go to the another important insight. This is the first insight. Okay, now we have understood the first insight. Now let us understand another important insight to the proof. The second insight is about additivity. What is this additivity is all about? Okay, so let us put a question and find out the answer for this. Why do the squares add up? Why do the squares add up? Do you have any answer for this? Okay, so here is a right triangle in which these are the squares on all the three sides. We are going to add area of this and then show that this is equal to this area. So we have got a question here. Why do the squares add up? I think this is a beautiful question. We have to answer it now. For this, look at this right triangle ABC, in which angle ABC is 90, AC is the hypotenuse, and say we have constructed a square ACDE on this. So draw the two diagonals also. You know that the diagonals bisect each other at right angles. So we have four right triangles are there inside. and all the four of them are congruent to each other because of congruency. And if you add all the four right triangles inside the square, that will make up the square ACDE. So the answer for this question, why do the squares add up? I think we got the answer now. It's because four right triangles inside a square add up to form a square only. Hence, squares add up to each other. Okay. So now further, what about the area of this whole square? Can we say that it is equal to 4 times any one of this right triangle? Therefore, we can conclude 1/4 the area of square ACDE is equal to area of the right triangle ABC. Therefore, another interesting point is there in this insight number 2, and it is the squares are proportional to the triangles. So the area of the square depends upon the area of the triangles. If the area is more, the area of the square will also be more. So therefore, hence, we could prove the Pythagoras theorem using these two insights only. Okay, that was the second insight. So there are two prerequisites are there to understand Einstein proof. Let us consider one by one. Let us take a prerequisite number 1. Okay. Here is a pair of similar triangles are there. Triangle ABC is similar to triangle DEF. What does it mean? It means that they have the same shapes. Okay. Now let us consider a ratio like this, AB by DE, which means that we wanted to compare the length of this segment AB with the length of this corresponding side DE. For that, we have to divide the length of AB by the length of DE so that we come to know how many times this AB is greater than the length of DE. So this is called by taking a ratio. So let us compare AB and DE. Similarly, the other pair of corresponding sides, and if you compare them, we will understand that AB by DE will be equal to BC by F will be equal to CA by FD, and that will be equal to a constant K called the proportionality constant. It means the length of AB is K times length of D. The length of BC is K times length of EF, and the length of CA is K times length of FD. For example, if AB is twice DE, then BC will be twice EF and CA will be twice FD only. So that is the meaning of the proportionality constant K. So in this case, we observe that K is greater than 1 because you can see the numerator has the sides of the triangle ABC, which are definitely longer than the sides of the triangle DF. It can be lesser than 1 also, provided in the numerator we write the sides of the triangle DEF. Friends, this is called AA criterion of similar triangles. Okay, this is called AA criterion as per our textbook. Okay, now let's go to the another important prerequisite number 2. Okay, this is something about the similar triangles only. Here once again we see the two triangles which have the same shape but not the same area. So therefore we write they are similar to each other. Now we wanted to compare the area of triangle ABC with that of area of triangle DEF. So for that we have to divide the area of this by area of triangle DEF. So we know that area of a triangle is half base into height. So there is no height here. So let us construct that. So let AM be perpendicular to BC and DN perpendicular to EF. And let us suppose that the length of BC and EF be 12 units and 6 units. And the two heights AM and DN be 4 units and 2 units. So now with this we can calculate the area. So the area of triangle ABC is this divided by this. On simplification, we get that area of triangle ABC divided by area of triangle DEF is equal to 4 divided by 1. Friends, you just cross multiply this. Triangle ABC into 1 is equal to 4 times triangle DEF. So, if the sides of the two similar triangles are in the ratio 2:1, then the areas of these two triangles will be in the ratio 4:1. That is, if BC is twice EF, then area of this triangle, the whole triangle, will be 4 times the area of this triangle DF. So that is what we have understood by considering the ratio between their areas. Okay, is it possible to connect this kind of a relation between the areas to the corresponding sides? Shall we try that? Okay. So what is the ratio between the two corresponding sides BC and EF? It is 12 by 6. It is clearly 2 by 1. So the ratios are in the ratio 4 by 1, but the corresponding sides are in the ratio 2:1. So in order to get 4 by 1, I think we need to square this. Shall we do that? So hence we say BC square by EF square is also equal to 4 by 1. So now we understood that the areas of these two similar triangles is 4 by 1, whereas the squares on the corresponding sides is also 4 by 1. Therefore, we say that area of triangle ABC divided by area of triangle DEF is equal to BC square by EF square only. So this can be put in the form of a statement as areas of similar triangles are proportional to squares on the corresponding sides. This is the theorem as per our textbook also. Okay, let us try to understand this theorem in a still better way. Here is a small attempt. So once again, let us consider the areas of those two triangles only. Let us apply the formula, simplify. So on simplification, we get BC by EF into AM by DF. Now let us make a small effort to write this equation in the form of a statement. Therefore, area of triangle ABC by triangle DEF is equal to ratio between the corresponding sides. BC by EF is nothing but ratio between the corresponding sides multiplied by the ratio between the corresponding altitudes. These are the two corresponding altitudes. So when you multiply these two, that will be equal to the ratio between the areas of the two similar triangles. On further simplification, don't you think we get BC into BC, and instead of AM by DN, can we write BC by EF only? How? How we could write BC by EF in place of AM by DN? Yes, we know that if two triangles are similar, then their corresponding altitudes will also be in the same ratio, which means if BC is twice EF, then this AM will also be twice DN only. Hence, we wrote in place of AM by DN, we can write easily BC by EF. Let us write it in the form of a statement. So ratio between the corresponding sides into ratio between the corresponding sides only. Okay, what is the next step? So simplify, we get BC square by EF square. So this we write it as, okay, ratio between the areas of similar triangles are proportional to squares on their corresponding sides. I think now the theorem is very clear to us. So now let us sum up this. So this is what we have understood now. So areas of similar triangles are proportional to squares on their corresponding sides. Friends, is it possible to write this proportion in any another way? Okay. Can you recall some of the properties of proportion, like invertendo, alterendo, dividendo, componendo. Can you remember that? Yes. Can you apply this it here? Okay. So we can write the same ratio as triangle ABC divided by BC square is also equal to triangle DF divided by EF square. This is called alternando. That is, this numerator is brought to the denominator and this denominator is taken to the numerator. For this proportion, it is better, it is worth to see the figure once. So area of this triangle ABC divided by this BC square, if you do it, it will be always equal to this similar triangle DF area divided by the corresponding side to BC, that is BC, that is EF square only. Okay, so now this is the new way of writing this proportion, which is called as alternando. And can we say that in the first step it is equal to k square? How? Since BC square by EF square means BC by EF into BC by EF. You know BC by EF is equal to k. So k into k became k square. Therefore here also we can write k square. So this is how we are viewing the areas of similar triangle theorem with the help of alternando. Okay, so now let us consider once again the same figure and write down the other two pairs of corresponding sides. Or we can split it like this into three ways and say that all the three proportions are equal to one another, and therefore let us write here it is equal to k square. Therefore each one of them is also equal to k square only. That means area of triangle ABC is k square times BC square. Area of triangle DF is k square times EF square, and so on. And the same thing can be applied to the other proportions also. Okay. So now we know this because of A criterion. We know that if two triangles are similar, then the ratio between the corresponding sides are in a proportion. But we just now understood that areas of similar triangles are proportional to the squares on the corresponding sides because of this wonderful theorem. Therefore, this can be further split up into three proportions and say that each one are equal. And since let us suppose that this ratio is equal to k. Okay, let us call it as k. That means the length of AB is k times d. Therefore here we can comfortably write that it is equal to k square, and therefore here also we can write that each one of them is equal to k square only. Okay, now so we got this and also this result. We have understood these two results. Now we will take each ratio one by one and cross multiply it with k square and understand a very important result. So this implies that area of this triangle ABC is equal to k square times AB square. Do you agree with this? So take this ratio and multiply, cross multiply with k square. We get area of this triangle is k square times AB square. So once again let us cross multiply this with k square. We get area of triangle ABC is also equal to k square times BC square, and it is also equal to k square times CA square. Also, now let us attend to this triangle DF. So in the same way, we can write the other three ratios. By cross multiplication, we get this. Okay, so this is the wonderful result which is going to help us a lot in proving the Pythagoras theorem. This is how Einstein has thought when he was just 12 years old. Okay, now let us proceed further. So now with these prerequisites, we can now understand beautifully the proof given by Einstein. So let us apply this theorem to a right angle triangle like this ABC, in which angle ABC is 90 and BD is perpendicular to the hypotenuse AC. Therefore, you know that this angle is equal to this angle and this angle is equal to this angle. Therefore, we have got three similar triangles inside the original triangle ABC. So, if you apply the theorem on areas, so we can write this. This is how we are writing in all the problems also in our textbook. But Einstein wrote the same thing in this way. It is worth reading. So, area of right triangle ABC divided by AC square is equal to area of this right triangle ADB by the corresponding square, that is AB square, which is equal to right triangle BDC divided by BC square also. So, and that is equal to K square only. So, this is how Einstein has conceived the concept of theorem on areas of similar triangles. I think we have done everything, friends. So let us find out areas of each of this right angle triangle one by one. On cross multiplication we get this. So area of right triangle ABC is K square times AC square. ABC means the whole triangle area is K square times this hypotenuse square. Whereas area of right triangle ADB is equal to K square times AB square. This one, area of this is K square times AB square, and finally area of this right triangle BDC is also equal to K square times BC square. Everything we have got now. Just hardly two more steps to go. Okay, can you guess what is the next step? Yes, so the whole triangle ABC is decomposed into two triangles, okay, two right triangles only. The area of these two is equal to the sum of the areas of these two is equal to area of this right triangle. Therefore, we say that area of right triangle ABC is exactly equal to right triangle ADB plus right triangle BDC. We know the area of each and every right triangles here only. So let us substitute that. So K square times AC square. It is equal to K square times AB square plus K square times BC square. Okay, what is the last step, friends? Come on, it's so amazing, you know. So that's all you're right. Divide throughout by K square only, so that we get Pythagoras theorem only. So hence proved. Wow, wow, great Einstein. So nicely you have thought of the areas of similar triangles in this way by writing just alterando for this, and you could get the areas of these triangles, and hence you can prove this. Hats off to you, Einstein. Okay, so Einstein has viewed the theorem on areas of similar triangles in a different perspective, that is by taking the ratio of areas of similar triangles to the corresponding sides, that is by writing alterando for the proportion, and hence immediately he could easily propose the proof for Pythagoras theorem. So great pranams to Einstein. Okay, hope you have enjoyed every bit of the proof. Thanks for watching the video. Namaste, friends. Namaste.